welcome to my presentation on predicate logic semantics. This is all about how we convert formal language into informal language. So how do you take statements that you've proven about predicate logic and apply those statements to the real world or the fake world of maths? Let's jump into it. Firstly, what is a model? This is the thing that we're going to be using a lot throughout predicate logic to define this conversion. So unlike AI1, the word model in math and logic is a little more well defined. It's got three parts, It's got a set called the domain. D, predicate logic formulae describe properties of this set. For example, the predicate logic formulae that is converted to all integers have a negative, the domain is integers, and then, there, for all integers there exists another integer such that b equals negative a, whatever. The second thing it contains is a mapping from functions in the signature to functions on the domain. So it says, for every function that is used in all the predicate logic formulas we're talking about, what does that mean as a function from elements of the domain to elements of the domain? So for example, if you had like f of x and y, it would be a function from two elements of the domain to one element of the domain, for example, plus. And finally, a mapping from predicates in the signature to subsets of d to the arity. So these are n-ary relations, so relations with the same arity as the arity of the predicate, where if, for example, p of xy is true, then the relation that represents p has xy in it. So just a reminder, predicates, they're propositions about elements of the domain. Let's move on to see what this actually means, though, like in a more less literal sense. So a model is a scheme to convert predicate logic formula into regular old maths or English or whatever, and it parameterizes the function that I'm going to call turnstile, where turnstile maps p onto human language with all its mess, and p is the Backus-Naur form for predicate logic, as we saw in Shay's predicate logic syntax presentation yesterday. Since predicate logic is a sound logic system, any syntactically valid formula is always true no matter what model you use. Which means that if we can find a good model to represent a system, for example, Gruff stuff or Minecraft Redstone or train timetabling, you can start using predicate logic techniques to prove things about that system, which is very cool and very nice. So why do we use relations for predicates? Well, especially in the context of binary predicates, it allows us to think about predicates like graphs, which is really useful, and with that we can get stuff like reflexivity, transitivity, and symmetry to be proved or used in our proofs. Relations are built off tuples, and tuples can be any length, so we can have any predicate arity. We're not limited to up to 5 arity. And also, as we'll see later, the definitions we use to define these predicates in our models can be really concise. They can just be, x such that our definition of x is true. So what is this turnstile function? I like to think of it as a recursive function on the syntax tree of an expression, where, for example, it maps a to b, if a then b, a arrow b onto if turnstile of a, then turnstile of b, and so then you would recursively apply turnstile to a and b and put that in the if-then stuff. That applies to and or as well, but if we have a look at the for all and exists things, it's slightly different. What we do is we define this value a, which is then shown, and then in our parameterization of our turnstile function, we say that a is the same thing as x, where x is some where x is used in a. So for all x becomes for every a something. And that's the same with the exists. And so then we recurse down the syntax tree, the expression, until we hit the base case, which we'll talk about in a second. So what do we mean by the base case of this function? Well, the base case is it would be models of a predicate. So if we take in just a predicate, we're going to replace it with what the model defines that predicate to mean. So for example, if we said p of x is defined as x equals 7, we would then replace p of x with these double square brackets around x of 7, which is a set. This double square brackets is another recursive function, very confusing, which is very similar to the turnstile function, but instead it replaces the functions in the it replaces functions in the signature with their definitions as given by the model, and then applies itself to the inputs to the function. So for example, if we had double square brackets of f of x and y, where f is defined as, for example, multiply, that would become double square brackets of x times double square brackets of y, and then the base case of this is where it's just replacing a single variable. And that's what this extra parameterization called the mapping does. The a becomes x, or that we saw from the for all and the exists on the previous slide. So if we so in the example we have on the bottom right, we're converting p to less than or equal to, and then f to plus, g to negative, and then x to a and y to b as shown here. So it's a recursive function whose base case, so the turnstile function is a recursive function whose base case is also a recursive function. So let's have a look at how taking one model in can, how we can use two different models on the same signature and the same predicate logic formula to get similar but different outputs. So we've got our signature that contains no functions, and the predicates p of arity 1 and q of arity 2, and our we're going to use the predicate logic formula theta. So theta is going to be defined as for all x, for all y, if q of xy, then p of x, then for all x, if there exists y such that q of xy, then p of x. Let's get started with writing out our definitions. So theta is going to be defined as for all x, for all y, if q of xy, then p of x. Then for all x, if there exists y such that q of xy, then p of x. So our first step is going to be an implication introduction. I'm going to take this guy here, this for all xy, if q of xy, then p of x, as our assumption number 1, which means that this is going to be our what we're trying to prove. So assuming that for all x, for all y, if q of xy, then p of x, then we have to prove this guy. So we're going to do a for all introduction, and x is not free in the output or in the output or any of our undischarged hypotheses, so this is legal. So then there exists y such that q of a and y, then p of a. Our next step is going to be a second implication introduction. Where which means our second assumption is there exists y such that q of a y. Now, does anyone know the rule of thumb that comes up when you assume existentials? Just a generally useful thing to do. Okay, the answer is, yeah, sorry, write the substitution? What I was thinking about was do an existential elimination immediately, because otherwise you start to make your proof a little more difficult than it needs to be. That should be up here. 3 existential elimination. Yeah. So assumption number 3 is q of AB, and we have q of AB, and for all x, for all y, q of xy, then p of x, and we're trying to get p of a. We can get that from an implication elimination. That's a mess. Using our assumption number 3 from our existential elimination. And this guy comes from assumption number 1. It's a terrible one. Using 2 for all eliminations, where we specifically choose to substitute x for a and y for b so that we can match things up ready for this existential elimination. And we'll start talking about the models we're using. So model 1 is defining the domain as the natural numbers. There's no functions in the signature, so we don't need to worry about any functions. And we're going to define p as x such that x is not equal to 0, because it's a unary predicate, so we don't need to put a tuple in the input. And we're going to define q as the relation xy such that x is greater than y. So in there, the tuple p and q is, sorry, the tuple a and b is in the set if a is greater than b. So we're going to take our definition of theta from over here, copy them over. So model 1 parameterized by, turnstile of theta parameterized by model 1, and no mapping. Okay, we're going to break down theta into its syntax tree, its expression tree. So firstly, there's this if statement. That's the outside, if that makes sense, because we've got the scope of the first for all and exists on the left side, and then the rest of the equation on the right, rest of the formula on the right. And then on the left side, it's going to have this for all on the outside, and then the exists under that. Sorry, and then the for all under that. And then finally this if statement that contains q of x, y, and p of x. And on the right side, it's got this for all. And then this if statement here, because this is one scope. And on the left side of this if statement, it's got the exists, and then the q of xy. And on the right side, it has that q of x. And so if we have a look, as we repeatedly replace parts of this equation with their modelized counterparts, their converted counterparts, we should start to see it follow this structure on the right here. So first of all, let's start by replacing this if-then and applying model 1 to both sides. And put brackets in to make things clearer. And so we've sorted this guy out. And then let's have a look at this for x next. So this would become we're going to and just to save time, we're going to go for all a in our natural numbers. And then it's going to be the turnstile of M1, where instead of an empty mapping, we're going to map A to X. Sometimes you'll see it as X maps to A. That's a pretty reasonable way of doing it. But it doesn't really matter. All that matters is that there's a correspondence there. And then we can do the same thing. And I guess put that back in there. Cool. And then let's do, so this for all x has been sorted, and continuing down in a leftmost conversion, or a pre-order if you want to think about it like that, we're going to deal with this for all y. So that's, we can simply modify this to say for all a and b in the natural numbers, and add b maps to y in here. And so next, we're going to sort out this if-then. So that would be if, since we've reached the base case on q of x and p of x, we can just replace that with our double thick square brackets. This isn't 2 square brackets in a row, it's like extra thick square brackets of q of x and y, with this same mapping here. You know what, I'm going to call this mapping lowercase m, just to save time. Lowercase m and m1. Then the definition of, welcome back. Then the double square brackets of p of x parameterized with the same parameters. And we can just put that back in here. And then we'll come back to the base cases in a bit, because they're slightly different, because they use the double square brackets, and we'll have a look at this for all x. We're going to do a very similar thing. We're going to add the x maps to A mapping down here. Get rid of this guy. For all A, or A maps to X to be in convention with the others. For all A in the natural numbers, whatever this is applies. So the for all A in the natural numbers, the conversion of there exists y such that xy, if xy then p of x. Sorry, if there exists y such that xy then p of x, and the conversion is parameterized using model 1 and A maps to x. We can then do this same thing to this if statement over here. So this would become turnstile of model 1 and A maps to x of there exists y such that q of xy, and that would be if this guy then double square brackets p of x parameterized by m1 and A maps to x. Work this guy out. Bring theta a bit off to the left. And then finally, we've just got to say there exists b in the natural numbers such that double square brackets of q of xy where A maps to x and B maps to y, but obviously that's what we defined as m1 little m over here to save us space, because it gets quite repetitive otherwise. That's our little m. And we can replace this guy with this guy. And now this is starting to look a bit more like a regular maths formula. So if for all a, b in the natural numbers, if q of x, if something, then something, then for all a in the natural numbers, if there exists b in the natural numbers such that something, then something. So looking at our model, we can see that, or we can mostly remember that q of xy is the same as x is greater than y, but x and a are the same. X on the inside is the same as a on the outside, and b on the inside is the same as so y on the inside is the same as b on the outside. So we can say that a is greater than b, and we can do the same over here. And then on the left, we can say that we know that p is x is not equal to 0, but according to little m here, an x on the inside is the same as an a on the outside. So we can replace this with a is not equal to 0. And the same, oh my god, over here. Any questions about that process? So, model number 2 is a little sillier, it's a little stupider. Our domain is going to be people in a friend group. I know, computer science students having friends, unlikely. There's going to be no functions, because there's no functions in the signature. Our P is going to map to a unary predicate, a unary relation on this set of people in a friend group, where it's x such that x is not single. I know, computer science students being not single, it's crazy. These might be like English students or something, I don't know. And then Q is going to map to x and y such that x is dating y. And we're going to quickly bash through converting this theta using model 2 to see how these two conversions would be similar yet different. So let's hop back over to showing my little doodling. So let's grab another copy of theta, put this over here, and it's, you know, its tree's not changed. So this is the turnstile parameterized by model2 and the empty mapping of this guy. So the if-then step is going to be the same for both, the same as before. So if this guy, if something, then something else. And the for alls and on the left side are going to be pretty similar. So if every person, if for every pair of people in the friend group AB, whatever the model's definition, with the mapping A goes to X, B goes to Y, except that's just little m because, you know, save time, save space, of this guy. So if for every pair in the friend group AB something, then for every person in the friend group, every person A in the friend group, if that makes sense. It's kind of a mess. Model 2 with A maps to X of this bit here. And as you can see, the same pattern is happening. We're going through and we are replacing things with equivalent text, basically. It might be more formal text in this case. You know, the slightly more shorthanded, that's a good way to say it, the shorthanded definition of for alls and the natural numbers and stuff. But really, it's just text, right? And this is slightly fancy text. It's not like the most human readable, but it's still just text. It's just a statement of fact that may or may not be true, and it is true because we've proved that theta is true and predicate logic is sound. And so again, the same thing. Let's just replace this with if q of x, y, m2 little m, then p of x, m2 little m, and we can do a similar thing here. If the turnstile parameterized by m2 and a goes to x of there exists y such that q of xy, then the meaning of p of x parameterized by m2 and a goes to x. This replacement stuff is the same. I hope you can notice that there's not really a difference here. The words are the same, but the words are different, but the pattern's same. And again, like we did before, we can say if there is someone B where the meaning of q of xy parameterized by m2 and lem in this case we can then replace this with A is dating B, this with A is not single, and this with the same thing. Not the I, cross the T. Does this conversion make sense? So if any pair of people in the friend group A and B, for every pair of people in the friend group A and B, if their A is dating B, then A is not single. Then for everyone in the friend group, if there's someone B where A is dating B, then A is not single. Does that make sense? And more importantly, can you see how these two concepts are fundamentally the same? If that makes any sense. So, and change to displaying slides again. Cool. The pattern we've seen in both of them is that we're defining what p of x is based off q of xy. So, for example, we're defining not equal to 0 as, there is a smaller number than this. We're defining that 0 is the minimum value. So, for every A, B in the natural numbers, if A is greater than B, then we know that A is not 0. So, if we've got that definition, if we're assuming that definition, then if there is a number, if you've got, for any number you have, if there's a smaller number, if you can find a smaller number, then you've proven that it's not 0. And it's the same thing for the Model 2 example. If we define not single as dating someone, if you take anyone in the friend group and you can find someone they're dating, then you know that they're not single. And this pattern, this fundamental structure underlying these two expressions, one about numbers, one about relationships, the pattern's the same, and they're both true because they both they're both like the semantic filling in of they're both meanings that have been given to theta, and we've proved theta to be true. This is like ridiculously powerful. If you can figure out how to convert anything into a model, you can start making proofs about that model. And there are a lot of standard things about predicate logic that have been proven anyway. There's probably a big list somewhere of proven predicate logic results. So I'm going to turn it over to you guys. I have got a formula xi, which is that's what that Greek letter is, where for all x, for all y, if p of x and f of y then P of xy. And this isn't a syntactically valid formula. We can't prove it. So there's going to be some models that create semantically valid statements, so true statements when you use them to parameterize the turnstile function, and some that aren't, some that are false. So we're going to call them mtick and mcross. So I'm going to turn it over to you guys, see if you guys can figure out some mtick and mcross. And the signature is seen in the top left. It's, our one function, arity1 f, and our binary predicate p. Valid, natural numbers, 0, true. Okay, so yeah, that would work. You're saying that like p of x and y is always true? Yeah, okay. Then yeah, that would totally be valid. So a function that does whatever, for example, setting it to 0, and then applies and then just says whatever x and y are, if you p of xy is true. Yeah, that's valid, because if true, then true is always true. Yeah. And do we have do we have an example of m cross or m invalid? That wouldn't actually be true, because if false, then false is true. Yeah. Because, well, I do have an invalid one on the next slide, so let's have a look at this guy. Our example of m cross is the following. So we got our domain being the natural numbers, and our function f is going to map x to x plus 1. And our predicate p is going to be x and y such that x is less than y. And this is a for all x, for all y. So if we can find one counterexample case, then we can prove this isn't true. One of these counterexample cases is x equals y. So it is true that x is less than y plus 1, because x is less than x plus 1, right? So p of x and f of y is false, right? It is true, sorry. But x is not less than x, right? That would be silly. If 1 is less than 1, and so p of xy is not true. So true then false, that's invalid. An example of our mtick is similar to Shay's example of p of xy is always true no matter what xy you have. In this case, our domain is just two elements, a and b, and our function x turns it into b, and our function f maps whatever it takes in as an input onto b. And p of x is the two pairs AA and BA. So we're saying that basically p of xy is true if y is A. But because f turns y onto b, we get false then true, and if false then anything, it's fine, right? We can use false elimination here, because p of x and f of y is going to be false, because it's going to be always x and b whatever y is, and p is only true when the second element is a, and since the first part of the if statement is always false, whatever we put afterwards is valid. It's fine. If I know that false, then I know anything else. Anyway, that's it. Thanks for watching. I hope everything makes sense here. If you've got any questions, give me a shout.